Now we're going to take a moment to talk about areas and lengths in polar coordinates. So the first thing we're going to talk about is determining the area of a fan-shaped region between the origin and a curve. So I've brought in a picture here. This is what we're going to be talking about, finding that fan-shaped area. So maybe some area here, this kind of region. Right, so we're bounded by this blue curve. That's what we're looking at. So what we can say is that if we are given some polar function, r in terms of theta, r being a function of theta, as long as theta is in between two bounds, alpha and beta, right? So that's our interval, our rotation interval, and our radius is a positive value. And also, beta minus alpha, the difference between those, has to be less than or equal to 2 pi. And what that means, we start at 0, we rotate around, we end at 2 pi. So this only works for one rotation. For multiple rotations, you would need to, find that one rotation and then add up the pieces or percentages of the additional space. And so we know that the area can be calculated. This is our formula. Area is the integral from alpha to beta of 1/2 r squared d theta. And so 1/2 r squared d theta, this is called our area differential. And that area differential could be defined as saying, well, dA equals 1/2 r squared d theta, or 1/2 f of theta squared d theta. So let's do an example. So for this example, we're going to find the area in the region, or the area of the region in the xy plane, which is enclosed by the cardioid. And a cardioid is a semi-heart-shaped curve. So the cardioid we're dealing with here is r equals 2 times the quantity 1 plus cosine theta. And so I've pulled in a picture of what this cardioid looks like. Essentially, what we are going to be doing is finding the area of this region enclosed here. And as we consider this, we know that to create this, we're starting at 0, and that radius makes this one full sweep all the way over to 2 pi. Okay, so this one full rotation from 0 to 2 pi of theta, that's what we're going to be calculating the area of. So this is a rather simple problem to set up. We defined our formula on the previous slide. But we would say we've got the area from alpha to beta of 1/2 r squared d theta. So in this case, my area is going to be the integral from 0 to 2 pi, 1/2 times the quantity 2 times 1 plus cosine theta, quantity squared d theta. Now if I square that 2, that becomes a 4, and the 4 and the 1/2 come out in front, so that leaves me with my area is equal to 4 divided by 1/2, or I'm sorry, times 1/2 divided by 2, is I have 2, the integral from 0 to 2 pi of 1 plus cosine theta, quantity squared d theta. So my integrand, I can square that, FOIL it. That gives me 2, the integral from 0 to 2 pi of 1 plus 2 cosine theta plus cosine squared theta d theta. And the first two terms here, those are pretty easy for us to integrate. The integral of 1 will become theta. The integral of 2 cosine theta will be 2 sine theta. And for the integral of cosine squared theta, when we're dealing with that, we use a double angle, which is 1/2, and that would be 1 plus cosine 2 theta d theta. So that's going to be 1/2. The integral of 1 is theta, and the integral of cosine 2 theta is going to be sine 2 theta over 2. So I have in here plus 1/2 times theta plus sine 2 theta over 2. Now we need to evaluate this from 2 pi to 0. So before I evaluate, I want to clean up in here a little bit. So I have 2 theta plus 4 sine theta. The 2 times the 1/2 goes away, so then plus theta plus sine 2 theta over 2. And of course, 2 theta and theta, that gives me 3 theta plus 4 sine theta plus sine 2 theta over 2, evaluated from 2 pi to 0. So plugging in 2 pi, I have 3 times 2 pi plus 4 times the sine of 2 pi plus sine 2 times 2 pi gives me the sine of 4 pi over 2 minus, and when I plug in 0, I get 3 times 0, 4 sine of 0 plus the sine of 0 over 0 over 2. And of course we know 3 times 0 is 0, so that's gone. Sine of 0 is 0, so those two terms go away. 2 pi and 4 pi are also going to be 0 terms. So our solution here is 6 pi. And that represents the area enclosed by that cardioid shape.